Good afternoon. I'm Professor Sever, and welcome to my video notebook series on linear algebra. This is part 3 of 3 in this notebook series. Today we are reviewing notebook number 1 on linear equations and linear systems. Let's begin. In our previous installment of Notebook 1, which was Part 2, we introduced elementary row operations and introduced some introductory examples where these operations were employed. So in the next section, we're going to go through this process of formalizing how we go about doing the solution. Right now, we're just introducing the building blocks. But nonetheless, there are two fundamental questions that we have. Existence, that's consistency. Is the system consistent? Okay, that means is there at least one solution, as we discussed. And is the solution unique, right? That means is there only one solution? Let me illustrate this in a tree. I'll illustrate the totality of conditions comprised by these two questions. And it's another way to envision the previous theorem. So it'll be a tree representation of this theorem. In our theorem on the nature of solutions to a linear system, we see that there are really only three cases illustrated by the theorem. So let's look at it in a tree diagram. So we know that for any linear system, you have only two conditions. So the first condition is binary, namely, the system is either inconsistent or consistent. And in the case of a consistent system, again, it's another binary situation. There are either exactly one solution or infinitely many solutions. And as we see, these cases are depicted in this binary tree, the totality of solutions indicated by our theorem. So let's return to where we were in our video notebook before we went back and reflected on this theorem. We were about to introduce the notion of row equivalence. So, another definition. Two matrices are said to be row equivalent if there is a sequence of elementary row operations that transforms one matrix into another. So, here I'm starting with this matrix, and don't ask why, but here we're going to apply these three operations in succession. So we switch row 1 and row 2. So if we switch these two, you can see that here. Okay, then on the next step on this matrix, I will apply this operation. I'll multiply row 1 by minus 5/2 and add that to row 3. Again, we won't ask why we're going to do this operation. Let's just do it. And of course, we're going to put the result back into row 3. If we did that, we would get the following. I leave that computation to the reader. For the third operation in this example, we will multiply row 2 by 1/2 and add that to row 3, putting the result in row 3. And if we did that, we would obtain the following new third row. And the point is then, this matrix is row equivalent to the final matrix. Why? Because there was a sequence of elementary row operations that produced this matrix from the original. And in fact, you could also say the initial matrix is row equivalent to each of these matrices in succession. It's row equivalent to the second matrix because this one operation, it's a sequence of one, produces it. Okay. Now, row operations are reversible. So, if we look at this example, and this is one of the examples that we did earlier today in this lecture, in this video lecture. So we did 4 times row 1 plus row 3, putting the result into row 3 produces a new matrix. By the previous definition, let's review the definition. The definition says a matrix A, that'll be the original one, is row equivalent to a matrix B, that's the resulting matrix, if there's a sequence of elementary row operations that when applied to A in succession produce B. So A is row equivalent to B. What about the symmetry? Is B then row equivalent to A? Well, and this is what we're kind of addressing here. Row operations are reversible. So if I could apply a row operation to this matrix A, which yielded B, here's one such operation, can you do it in reverse? Can we apply a row operation to B to get A? In other words, can you undo the effects of this operation? The answer is yes. So let's take this matrix. You can see I've written it here. Here's the B. I'm going to apply -4 row 1 plus row 3, put the result into row 3. Let's see what we get. So let's check it. Let's check this mentally. -4 times 1 plus 0 is -4. -4 times -2 is 8. 8 plus -3 is 5. -4 times 1 plus 13 is 9. And finally, -4 times 0 plus a -9 is -9. So this is just an illustration, but this is in fact a theorem, which means it's provable. So it holds for all three of the elementary row operations. So each operation is reversible. So if two augmented matrices are row equivalent, then they have the same solution set. So this is really important. What this says is, remember, row equivalence means what? Well, it means that you would achieve one matrix from the other by doing one of those three things, the three elementary row operations. These are the only three operations that we have. And it turns out what it says is that it doesn't change the solution set, which is excellent, if they were going to be the tools that we were going to use to find the solutions or solution set, and they will be. So these three operations will be the operations that we use to find the solutions of a linear system, because they don't change the solution set. The solution set is invariant under these operations. I'm Professor Sever. I hope you enjoyed this video notebook on an introduction to linear systems. Please look for my next notebook in this series. Thank you for watching Notebook 1 in this notebook series. This video notebook lecture will continue, so we look forward to seeing you there. I hope you enjoyed this notebook series. I'm Professor Sever. Thank you.